Good afternoon. Nice to see so many friends and so many alumni back for the occasion. So my name's Richard Wilden, I'm the Deputy Head of the Engineering Department, and I'm delighted to welcome you to this year's Jenkin lecture, where we celebrate everything special about Oxford engineering. And today's Jenkin lecture is going to be given by Professor Constantin Coussios, who I'll hand over to in a second. So he's the Director of the Institute of Biomedical Engineering. For those who don't know, we have Institute of Biomedical Engineering that physically sits up on the Old Road campus and is the intersection between engineering and clinical sciences. And it's really a fantastic example of how cross-disciplinary research, not just within the engineering space, but with engineering and the medical sciences can work. It has a long history of entrepreneurship and innovation. I guess its roots started about 40 years ago, actually, with Sir Mike Brady, who was a sort of a trailblazer in many respects in information engineering, robotics, and other areas. And really now the institute up there has grown to about 30 academics, engineering, physics, material sciences, as well as many clinicians as well. Constantin himself has been involved in many entrepreneurial activities. I won't embarrass him too much, but he's been very successful in the foundation of Organox, which is a wonderful example of how cross-disciplinary science and engineering can work, and is leading to really positive outcomes for organ usage and prolonged life of organs outside of the body. But not satisfied with his wonderful achievements, Constantin, I think 3 years ago now, 2022, instituted the Podium Institute, which Constantin is going to talk to us more about today. With that, I'll hand over to Constantin.
Thank you very much, Richard, and a very warm welcome to everyone. I would like to start with a video, maybe two.
You feel good? Yeah, I'm not feeling this fine.
Roman Grosjean that has gone into the barriers there.
Roman went with the front of the chassis underneath the barrier.
It was just as we were emerging from COVID in 2020 that I got to meet a very interesting man who approached Oxford with a very interesting challenge. Could we actually set ourselves on a journey to achieve what he felt he and others had achieved in the past 45 years in Formula One? Taking it from a sport that no country in the world wanted to host because they were on the order of 10 to 20 deaths a year, to one where, in his own words, it is today safer to drive a Formula One car at 200 miles per hour than a Mini down the M40. That challenge and the societal impact that it can potentially have on the 27 million adults and 3 million children who annually take part in sport in the UK is what gave rise to the creation of the multidisciplinary Podium Institute at the University of Oxford, hosted within engineering science. Its objectives were simple. Firstly, produce world-leading science to inspire and forge evidence-based changes in policy and regulation. But the unique twist is not with an emphasis on the professional sport, but rather on the community, youth, and grossly underserved female sport. Secondly, we realized very quickly that we couldn't solve problems unless we could measure the things that mattered. And therefore it is intimately intertwined with the development of innovative technologies to analyze, monitor, and prevent sport injury. And thirdly, we didn't feel we could rely on those measurements unless the devices with which we made those measurements had a guaranteed standard, and we could therefore believe the numbers they were giving us. Those three key objectives gave rise to a vastly interdisciplinary approach that stretches beyond engineering into all corners of the university, And I'm summarizing here only a very small subset of the skills we have had to bring to bear on this journey in its first 3 years. Anything ranging from sensor engineering and wearables, all the way through to the now ubiquitous machine learning and AI, but also computer vision, finite element modeling, down to proteomics and metabolomics, as I will show you. And that has given me the pleasure of assembling an incredible team, of which I'm merely the conductor. So the research I'll be presenting to you today is certainly not my own research, or not exclusively my own research. It's actually the work of a broad range of individuals, particularly the 4 individuals circled in orange. Our Professor of AI for Sport and Soft Robotics, Professor Liang He, our Professor in Wearables Tech, Professor Mara Villarreal, and our Professor of Brain Health, who recently joined us from the US and is here actually with us today, Professor Johannes Wickenmeier. But we have reached far and deep across the wonderful things that Oxford has to offer, into clinical neuroscience, into anatomy, physiology, and genetics, into brain science, into neurocognitive and neuroimaging centers of excellence in order to bring this together. So I will first of all try to introduce some of these key technology elements, because the title of the talk today is "What is the tech making sport safer?" I can tell you that my personal motivation in getting involved in this is both as a father of 3 boys, very sporty boys, and also as a 9-year governor of Magdalen College School, where what I encountered is that one of the biggest challenges encountered by parents, governors, and professionals in education today isn't always the academic side of education. It's rather what to do and how to manage parental expectations for safety and involvement around team sport. And this has actually been one of our key guiding lights in developing this program, is not how can we develop solutions that are present and available for the professional sport where resource tends to not be an issue, but how can we develop scalable, low-cost, adaptive technologies which for less than 5, 10, 15 pounds per child can potentially be scaled at a national and international level to really address some of the safety limitations. Being engineers, we would always start with modeling, and I've been very fortunate to have the chance to work for many years now with Professor Antoine Jérusalem in the Department of Engineering Science. Now, Antoine will spend a long time telling you how many millions of voxels his finite element modeling of the brain actually has, but the thing that is really exciting about it is that it can model at the adequate resolution all of the important structures in things like the brain. It can resolve white matter, gray matter, the interfaces with vessels, neurons, the neuronal paths. And because his modeling has been optimized now over many years, we're able for the first time to simulate in real time, on a personalized level, exactly what pressures and shear stresses are deployed within the brain at the precise moment of impact. The only problem we have right now is we don't know what those forces at the moment of impact are, and more about that in a minute. But those maps of the brain allow us to identify in a particular impact which regions of the brain are excited, and those regions are typically responsible for certain behavioral patterns. So if we can actually relate the physical to the intellectual, to the cognitive, we are probably on our way to identifying what causes brain injury and also how we might resolve it. A second key technology under the broad leadership of Professor Andrew Zisserman in the department and many others is the rapidly emerging field of computer vision. Now, I have great fun presenting this to rugby players and telling them, you're really a hot dog. Now, they love it, but the reality is that what's clever about this image is on the left here, you have 2 and only 2 photographs of that hot dog taken from 2 different angles. And it is possible using computer vision and extrapolation techniques to actually recreate the 3-dimensionality of that object using this limited number of views. And it's all well and good if the only asymmetric thing on your left is the mustard. It becomes a lot more challenging when you have a highly unpredictable object that actually starts moving around and has high levels of asymmetry, like the fern tree on the right. A third degree of complexity is that athletes tend to breathe, and that makes them highly deformable when things are going well. And therefore, you can see here a bird from a single camera angle that gives us multiple views. Well, that bird can then be reconstructed and manipulated using these computer vision techniques, enabling us to recreate three-dimensionality out of a limited two-dimensional field. And so, a few of the things that has enabled us to move forward in recent years is that today you can't go to a school match without at least 5 parents videoing the match from different angles. At least 2 poles of a GoPro or Halo or equivalent technology having been set up. And what we're seeing, therefore, is this proliferation of low-cost video technologies. The only thing is that they're today being dealt with as independent data streams. What if we could actually take all of those data streams and from the point of view of multiple angles actually make something of it? And here are some of the things we have been able to make, and I'll be referring to them on a few subsequent slides as well. On the top left, you can actually see a footage from World Rugby where the algorithm is automatically recognizing which player is involved in a particular collision. But also if you look at the color coding, sort of dark blue is left foot, light blue is right foot, we can actually identify specifically which body part of which player with what velocity is actually impacting on the specific athlete who's about to be on the ground. But there is a challenge. You will notice that the algorithm is still failing for the person we care about the most, the person who is on the ground. And that is because they are obscured. And because they are obscured, we need to have a way to reconstruct what is happening to them from the limited multi-angle footage that I was just describing. That's what makes them the hot dog or the breathing bird. The second aspect in the middle of the image is pose estimation. We can actually now identify specifically what angle the body is at the precise moment of impact and what the biomechanics between the different limbs are. And the third image on the top right is actually my favorite, because one of the things that really surprised me when we started working in this field is quite how important anonymity is in sport. It's important in all cases of medical or biomedical data, but of course the one thing you cannot anonymize when you have famous football players, tennis players, rugby players is video. And that's creating a massive impediment to clubs, broadcasters being willing to share large data sets because there is a concern that a particular professional athlete might be identified or blamed for having done something that wasn't quite right to a fellow athlete. So this technology on the top right is one of the world's first developed in collaboration with a computer vision lab that completely anonymizes video data whilst actually maintaining the important aspects of motion. So we're able to recreate all of the pose, all of the action, but essentially all shirt numbers, facial features, and anything that might render those individuals recognizable is now gone. And where we're moving slowly, because we've only been at this for 2 years now, is how we can actually take these multiple camera angles to create the 3D reconstruction that you see on the bottom left. Because ultimately, what we want to achieve, and this is very much in the works, is a completely anonymized 3-dimensional image of an athlete, down to the creases of the shirt, but without making it possible to identify whether they're male, female, or who they actually are. The next really interesting platform technology is medical imaging and neuroimaging. And I will show you something in the field of head injury, which wasn't my field up to 3 years ago, that really shocked me. If there are any real doctors in the audience, they will tell you that head injury is characterized using something called the Glasgow Coma Scale. And all you need to know for the purposes of this slide is that the lower the Glasgow Coma Scale, the worse the news are, and the higher the Glasgow Coma Scale, the better the news are. So 15 is a pretty mild head injury, but 3 is pretty serious trouble. Now, the majority of injuries today are diagnosed using CT, using a 3-dimensional reconstruction of X-rays directed at the brain that can primarily detect bone and also the pooling of blood if there is internal bleeding. that is a structural measure of injury. Have we actually altered the structure of the brain in some significant way? And what you will see here is that you actually have two people with Glasgow Coma Scale 3, a really serious injury. And I hope you will notice that their images look rather different. I think pretty much anyone would have been able to tell you that this is a very, very bad injury. It's, however, remarkable how closely linked those two very different scales of injury are. So we and others contend that concussion, one of the main topics in sport today, is actually really difficult because today it is an enemy we cannot see. We cannot see it because we've been looking for it for 25 years in structural images. But concussion is a functional deficit, and the research and clinical world of imaging and neuroimaging has come a very, very long way. And what you'll hear me talk about today is MRI, magnetic resonance imaging, and the use of functional MRI to be able to identify which regions of the brain actually light up functionally when a player has undergone a potential concussion. We can even today measure individual concentrations of brain chemicals non-invasively, as well as identify small microbleeds or disruptions in the axons and the neurological signal transmission in the brain. And in order to do this, we have been helped by two major advances in the last 20 years. The fact that this can only not be done statically, but that we have gained access for the next 2.5 years to the UK's one and only 3 Tesla mobile MRI. And I will talk to you about a study, a first of its kind, where we are taking this mobile scanner for the first time to female and male rugby players so they can be scanned within 2 hours of injury. So some of the interesting images that can be created, as I said, loads of different modalities, and I won't go through the detail. But one of the first things we started as the Podium Institute is to take our researchers and using the unique facility Richard described, the fact that this institute is actually based at the heart of the clinical site in Oxford. We can benefit from both the John Radcliffe and the Churchill. And within a few months of starting, we actually obtained an ethical permission to scan up to 120 11 to 18-year-olds who have undergone a suspected sport-related brain injury at the John Radcliffe with functional magnetic resonance imaging. We have spoken to all the local schools, all the local academies, and if there's anyone here today who'd like to find out more about this study, please come and see me afterwards. And so these are some of the really exciting images we're now starting to see. We have scanned out of 120 the first 47 patients in just over 6 months. And you can see here something called tractography that actually tracks white matter and the pathways of white matter inside the brain. And very excitingly, between a healthy control, so we're scanning 11 to 18-year-olds who've not had any suspected head injury, and 11 to 18-year-olds who've had a confirmation of a mild traumatic brain injury, we are actually starting to see not so much structural, but primarily functional differences in the way their brains are responding shortly after. The idea, we are fully aware that we will never be able to scan every single individual on what is very expensive fMRI. But if we can use it as a gold standard to validate some of the other things, computer vision, wearables that I'm about to show you, then we have a path to making it the flow of patients into the emergency department and the return to play a far more positive experience. And so speaking of wearables, we have 3 other key technologies that are really changing the game. The first of these, perhaps most significantly, and I'll tell you a lot about these, are wearable mouthguards. They've been in the press a lot recently. They are effectively inertial wearable mouthguards that allow you to know the linear and the rotational acceleration in the middle of the mouth. And they're being used increasingly by contact sports like rugby. They've been mandated now by World Rugby and the RFU to try and characterize not only the violence, but also the history of impacts called the player passport that a particular athlete is exposed to over the course of a season. Alongside those, we of course have the whole array of wearables that have been enabled by smartwatches and mobile phones. and a growing array of slightly more intelligent healthcare accessories like portable EEGs, electroencephalograms, and ECG, electrocardiogram devices. And so if we start bringing some of this together, here is an example. We're now working very closely with GB Snowsport. And here is a very good example of that sort of integration of these different things. So you will see someone doing something I strongly discourage you from trying at home. They are wearing an instrument and mouth guard. You will see their linear and rotational acceleration on the graph on the left. And at the same time, what a finite element model, in this particular case in collaboration with Imperial College, can actually make of that data in real time. So precisely at the moment of impact, we can now for the first time measure all those accelerations in a patient-specific way. It's no longer a model. They are actual measurements of the inside of the head at the moment of impact. Those linear and rotational accelerations are fed into the brain model that then produces a short-term disruption of the stresses, strains, and intracranial pressure that the brain experiences. That's great, that's an engineer's dream, but if you meet a clinical neuroscientist, they'll tell you, so what? What does it mean? What does it actually tell you? And that's where the neuroimaging component that I just showed you becomes very, very important, because unless we can somehow relate the physical with the medical, we will not have the impact we can have. A second example of wearables, so in this particular case, a simple heat camera. And very interesting that the temperature during exercise can actually be correlated directly to the heart rate. So Mauro here has been able with his team, completely non-invasively, to actually identify the variation of the heart rate between intense exercise and rest without any invasive sensors. And this becomes particularly important if we move away from brain injury for a second in the context of exertion. And in the context of exertion, we can directly, using these video metrics, not only do pose estimation, not only measure heart rate, but also start looking at oxygen saturation and the quality of the ventilation of the athlete. Are they actually running out of lung function? Are they actually undergoing hypoxia that might impact the recovery from training or from the matches the next day? All of that without them needing to wear anything. And that's where it's getting quite excitable. I'm sorry this sits in the wearable section. Another very important aspect of all of this is what happens physically, yes, cognitively and from an imaging perspective, yes, but also in the blood and saliva. And there are things that change during injury that are actually directly measurable. This is from a collaboration we have started with Abbott, the large international biomedical company. And they identified several years ago that there are certain proteins that vary in concentration in the bloodstream if some type of brain injury happens. But the problem is they vary very differently on timescales of minutes, hours, days, weeks, and months, years. Two of those, the most important, are S100B, that is a measure of blood-brain barrier damage. That actually means that we all have a coating in the vessels in our brain that prevent the brain from receiving infection. Under certain conditions, that barrier opens and actually lets stuff in and lets stuff out. It's very often taken as an example of pathology. It's also sometimes necessary when trying to deliver, for example, cancer drugs to the brain. So blood-brain barrier damage is a very, very important potential mechanism. UCHL1 is an indicator of neuronal injury, and GFAP is a very strong indicator of neuroinflammation, of some sort of inflammation. And then, longer term, you have all the proteins that many of us will have read about that are believed to be getting deposited and play a particular role in dementia, and I will tell you more about those a little bit later. So what's the name of the game for us? Can we, as technologists, work with the people who really understand brain and who really understand brain biomarkers to make it possible at the point of care to measure certain things in the first few minutes or hour of injury that tell us with certainty whether A 13-year-old student needs to go to A&E or doesn't need to burden A&E because they've not had a dangerous injury, and can also tell us several days, weeks, months later whether they can safely return to play if they have had an injury based on some sort of quantitative metric. And in order to do that, we have had to do two things. Work with Abbott to develop a point-of-care diagnostic. So this is a little cartridge that requires from a finger prick 1 droplet of blood and can actually measure those two variables. Now, this is where it gets exciting for me, because an fMRI mobile lorry sat in a rugby field will set you back about £5,000 to £10,000. This cartridge is available today on the NHS supply chain for £12. And it will only come down in practice over time. The problem is, we have the technology, no one yet knows what it means. We actually need to validate it against what it tells us for the short term, for the medium term, and the long-term recovery. And I'll also tell you one of the most wonderful, I've been in Oxford now for 23 years, and there's one thing I know nothing about Oxford. It continues to surprise me every single day. So we were then challenged as to why would you only measure the two things for which there is a sensor? What if there is something else that varies in saliva or in blood that is perhaps more difficult to measure, but is actually much more predictive and much more significant? And so we came across a very interesting technology from a company called Alamar Biosciences called Neulisa, and that is effectively a way of measuring 120 proteins that effectively completely dominate the central nervous system and seeing what all 120 do. And the second we discovered this, we said, we don't care how expensive it is, we have to collect data using those proteins. And our concern, of course, was that we would have to, in the current era of administration, place samples in test tubes and ship them across the Atlantic for them to be analyzed. And shipping biological fluids is not fun if you've ever done it. At which point the Neulisa CEO turned around and said to me, oh, you need not worry about that. Our worldwide lab is sitting in the building right behind yours in Oxford. So we had the world's foremost proteomics lab literally adjacent to the Podium Institute, and we didn't know it, and we're now working extremely closely together to analyze these samples across sports. And lastly, I think you would lynch me if I didn't mention the word AI once. I'm not going to measure the word AI very much because it's pretty much present in all of these things, how we analyze images, how we perform computer vision algorithms. But the one thing that is very exciting as a vision that AI will hopefully enable is as all of these things become validated, we want to create a model of the digital athlete or the digital twin. What that means is we want to be able, rather than have to wait for 5 years to see if a particular rule change in football or in rugby or in snow sport is actually going to have the biomechanical impact we hope it will have, is to start building a sufficiently advanced model that is validated and can predict whether those interventions, whether new methods of personal protective equipment, whether new wearables, new sensors, will be able to have a significant impact on a suspected injury. So how do we bring, or how do we hope to bring all of these technologies together for real societal impact so that they don't become the musings of a bunch of engineers? Well, one of the key challenges today in the world of sport and in the world of education is brain and concussion. And it was unavoidable that in our initial limited set of priorities, that had to sit very, very high on that list. And I really like this analogy with radiation. It's extraordinary to me that barely 200 years ago, even scientists who ultimately helped us understand radiation lived above radium factories. And they knew that something was wrong, but they didn't know what. They could sense that there was something not quite right, but they were really finding it difficult to pinpoint exactly what was causing the damage. And it took scientists the better part of 100 years to actually identify what in nature causes harm to human health, because everything in nature produces radiation. And it wasn't until we developed a low-cost, ubiquitous way of quantifying that dangerous part of radiation that it became possible for the very first time to identify safe and unsafe ranges for human health. And I would put to you that this is exactly where we are today in the space of brain injury. We have essentially a lot of data that suggests something isn't quite right, but not all head injuries and not all head impacts cause harm. For every case, for every identification of potentially harmful impacts, we can find an equivalent number of impacts of the same amplitude and intensity that do not cause that harm. So the question is, what is it about the combination of linear and rotational acceleration in the brain, and what makes us individuals as humans that translates into a short-term, medium-term, and long-term danger to our health? So our strategy around concussion fell in 3 buckets. First of all, we worked with government for the first time to produce the UK's first report on the incidence and economic burden of concussion across all major UK sports. It all starts with health economics. And what we learned, and this has just been submitted for publication in a major medical journal, that if you look at the major sports, they impact concussion in 2 ways. They either have a very high incidence or they have a very high participation. So rugby union, rugby league are 2 of the sports with the highest reported incidence, but their overall impact on the NHS is relatively modest because nationwide participation is only around 700,000 athletes a year. Swimming, which you might be surprised features on this list, has got an almost immeasurably small probability of concussion, but more than 5 million people a year do it. So it doesn't take a very high incidence to start having an impact on the NHS. And so we listed here those sports that cause more than 1,000 concussions a year. That's how we defined it. And what we learned rather surprised us. Today, almost all sports put together cost the NHS on the order of £362 million a year in A&E visits in the first year of injury. So this is not accounting for a potential link to dementia or longer-term health consequences. This is simply in the 12 months after a suspected injury. In fact, over 30% of people who show up in A&E show up because they have had a suspected concussion, and it's particularly parents who rightly worry about how to manage a potential injury in their child. So in the range 3 to 15-year-old, that proportion is even higher. That figure is only going to grow because rugby, we know, has a certain incidence of concussion because they've been surveilling it for 20 years. There are several sports that haven't even started. And so what we're trying to forecast in this model is exactly what will happen as surveillance grows to the same steady state as it has in rugby. And our prediction then is that it will be closer to 600 million a year in today's terms. And that, to put things in perspective, is about 20% of the cancer budget for a preventable injury. So this is something we have to address as a society, not only for standard of living reasons, but also for cost sustainability reasons. The second is we realized in performing that literature review that we know remarkably little. There are several sports that have no data. For example, gymnastics only has data in children, but none in adults. The data in women across the board is virtually non-existent. And as we start putting these things together, we realize that there wasn't a single sport where there was a data set where a cohort of athletes had been followed from relatively early to right before injury, to right after injury, to later in life. As evidence of that, I will tell you that NHS coding, which is what you write on the A&E form, doesn't even identify sport-related injury as a code. So today, if we want to find out someone had a concussion 25 years ago and that today they have some other brain pathology, that link cannot be made because the data does not exist. So we decided to start filling that gap as the Podium Institute as Oxford, and I'll tell you what we've been doing to fill this data set gap. But ultimately, the dream is to create a future where, a little bit like the Geiger counter, a little bit like radiation, there is a simple, intuitive scale that can account both for severe short-term head impacts and repetitive longer-term milder impacts. and be able to tell athletes, coaches, and medical professionals whether you're a 1 and you can continue playing, whether you're above a 3 and you need to go to hospital immediately, and at which point you might actually be ready to return to a normal training load. So I've already told you about these technologies, and we put together a program that makes it possible for the first time to measure exactly what is happening using wearables during impact, using those wearable mouth guards that quantify the linear and rotational acceleration in the brain. Contactlessly, what happens during impact by being able to identify the full boundary conditions around the moment of impact. Pitch side immediately after impact using 3 Tesla MRI mounted on a humongous lorry, as well as biomarkers, measures of neck strength, eye tracking movement, intracranial pressure, and ultimately being able to take these measures together to forecast the short and longer term consequences for that particular athlete and compare it to the gold standard, which is neuroimaging. So a lot has been written about mouth guards, and next Thursday, Friday, we'll be running the 2nd annual Podium Institute conference here in Oxford, where the world's foremost experts will come and tell us about mouth guards. This, for just a moment, is my own personal view of them, and I'll let you be the judges of what informs that personal view. These are 3 fantastic publications from Equestrian, and you're seeing a bunch of red dots and a rotational velocity on the y-axis and a linear acceleration, rotational acceleration and linear acceleration on the graphs above. The red dots are concussive impacts. The blue dots are non-concussive impacts. Can anyone in this audience place a horizontal line on the graph that will tell apart the red dots from the blue dots? So my view is that for as long as we're looking for a magical threshold from an instrumented mouth guard to tell us whether a player has been concussed or not, we are not going to find it. And the reality is that those thresholds, we know as engineers, cannot possibly be the force. It has to be the energy transmitted to the brain. If there is a mechanical quantity that matters, the factor of time really has to matter somewhere in that equation. So we are now collecting these signals, and it is wonderful that we have these sensors, but we need to find a way to convert what they tell us into a diagnostically meaningful quantity, which we have not yet been able to conclusively do. So the mouth guards will hopefully tell us in real time and in 3 dimensions exactly what the force time excitation diagram is for that particular athlete. We will then be able to plug them into Antoine's model to give us a 3-dimensional map of where the brain has been stressed, and then be able to compare it in 3 dimensions to functional neuroimaging that will tell us whether the regions that have been stressed are now starting to perform differently functionally. Alongside that, realizing that neuroimaging is something very expensive, we're also looking at all of these other technologies that are much, much lower costs. So we now have access not only to the mouth guards made by a company called Prevent, but also to wearable EEG. We can actually perform a wearable electroencephalogram in about 45 seconds pitch side. That actually tells us about the electrical activity and the transmission of electrical signals in the brain. We can measure pupillometry and also eye tracking using a VR headset. We can also measure balance and the alteration of balance. And those are exciting, not because they're particularly clever, but because they're low cost. So if in combination they can tell us what the neuroimaging tells us, we are onto a winning formula. And so, on the 15th of May 2025, the university sponsored the world's first real-time acute phase of injury multimodal study in female and male rugby players. So we actually, for the first time in history, are going out there with 30 female athletes at Gloucester Hartpury and 30 male athletes at Gloucester Rugby Club. Why Gloucester, you ask? Well, it's within an hour of Oxford, and it also happens to be co-located with the epicenter of mobile MRI, a company called Cobalt in Cheltenham. So it was a very happy intersection of circumstances, and they have a pretty good women's and men's team in the same club. And by putting those things together, what we've now been able to do is I personally briefed the players on the 18th of July. And it's very strange as a scientist to be talking to a room full of 18 to 25-year-old professional athletes because you have no idea how they're going to respond. And it's fair to say that I was looking at cold stares for the better part of 20 minutes. And I thought, I'm not doing very well here. And at the very, very end, it occurred to me to just say, I couldn't ask them if they want to take part in the study or not. That was completely unacceptable from an ethical perspective. So I said, so broadly speaking, who here thinks this type of study is a good idea? And that very cold room, there were 52 people in it, 50 put their hands up. And for the first time ever, I think because we're running it as an independent institution with the credentials we have, because they now believe we care for them, not for their club, not for the sport, not for the governing body, they're actually, all but two are actually taking part. And that is a remarkable achievement of what Oxford can do when it sets its mind to it. So these are scans from one of the 30 athletes we have already successfully baselined. We have not yet analyzed them because the whole point is to have that baseline, and then we will follow them for all their home and away matches, whether at Kingsholm or elsewhere. And the second one of them has a suspected injury. We will now, for the first time, be able to look at the differential between what happens within 2 hours of injury and what was good for them in August before they had started training. Now, that takes care of the short term, but of course, what the world really worries about is what is the impact of those impacts, not only up to the point where the athlete returns to play, but what happens to them later in life. Well, what happens to them later in life is very much the subject of study of Johannes Wickenmeier, who's here with us and whom I will encourage you to meet after the lecture today. And what we see is that there is an impact of impacts on the brain on different length scales over very, very different time scales. We see things like ventricular enlargement, cortical thinning, hippocampal shrinking, sulcal widening, all of which are traits and features that tend to predict or foretell a pathology that is about to set in the brain. So how can we use these? There is, as I mentioned earlier, an evolution of different time scales of misfolded proteins that seem to be highly associated with neurodegenerative diseases. So Alzheimer's being one of the most common, amyloid and tau protein have been long suspected to play a very significant role, but we don't really understand why. And we don't really understand how different pathologies relate to the time course of these proteins. What we do know, however, from measurements is that each and every disease has got its very own time course and its very own relationship with age. So what Johannes and his team have been doing is looking at how these mechanical markers, the things we can actually predict from engineering brain models, relate to these different pathologies and to normal cognitive function, mild cognitive impairment, or advanced pathology like Alzheimer's disease. And he has started, as part of the Podium Institute, this extraordinary work, which is, we have, of course, this challenge. We want the answers now, but these models need to be validated against tens of years and large data sets with imaging and neuroimaging in order for us to be ready to believe them. And so he's now been able to identify 70 to 75-year-old cognitively normal subjects with scans that are 4 to 5 years apart, and start aligning what this model is predicting to the decline or non-decline, development or non-development of these particular subjects. And what we hope this will do for us is that as we start having these unique data sets of exactly what has happened to the brains of these players in their active years, we can then start projecting them onto the future and continue refining the models as those players remain involved with the research. But this makes this not a one-year project, not a 5-year project. It makes this a 50-year endeavor to completely change the face of sport safety. And we're just at the start. We are, by the way, here in one of the world's most oldest brain banks. So St. Hugh's College, as I learned from Antoine, who's a fellow there, was used as a First and Second World War hospital particularly for veterans that had suffered blasts. Those veterans donated their brains to St. Hugh's, and today we have one of the largest brain banks with complete history of injury. There is a remarkable amount of interplay between army vets and athletes, and therefore what we're doing is trying to use the military data that precedes it to start getting some early validation and hopefully start supplementing military science with sports science as we acquire greater data sets. So we are just at the start of what will be a very long journey, but we now feel we have a better understanding of what we know, but also the failings of the past. We're doing our very best across not only rugby, but also snow sport, equestrian, football, tennis, to start filling in those data gaps that exist amongst and across age groups and across genders, and also trying to create a strategy for safer sport for the future. We would, of course, not just like to predict and understand injury, we would also like to be able to prevent it. And one of the key areas where engineering has a huge role to play is in understanding and characterizing the huge variety of sport-induced head impacts. So depending on what sport you play, we are pretty sure it's not one head injury. It can't possibly be the case that all of these different sideways lateral frontal impacts actually result in this one ubiquitous thing we call concussion and mild and severe traumatic brain injury. And so one of the things that really surprised me is there is this general accepted wisdom, which is not proven, that the higher the linear acceleration and the higher the rotational acceleration, the greater your probability of traumatic brain injury. Intuitively, it makes sense. The more severe the impact, the more likely you are to get into trouble. What is more surprising is that helmets, I learned when I started working on this, have really been designed to protect the head against skull fracture. They have never, in their overwhelming majority, been designed to protect against concussion. And that translates itself as follows. A helmet will reduce the linear transmitted acceleration by about a factor of 7, but it will barely dent the rotational acceleration by about 10 to 20% on a conventional helmet. And increasingly, we have evidence that it is shear rather than compression that causes the majority of what we call brain injury. So conventional helmets still have, with the best case scenario, about a 75% probability of concussion. Some of the interesting advances, including MIPS and wave cell, are being quite successful in reducing that probability of injury. Why? Because, as I said, most helmets are designed to be able to absorb compression, but what we now need are helmets that are capable of absorbing shear. So as the head rotates against a solid surface area, we need to be able to take away some of that rotational energy. And in the team of Liang He, Chening Yu, an independent research fellow, has been doing this wonderful work with these three-dimensional pinned models that are now starting to show great promise as a way of reducing head injury. I've also had the opportunity to work directly with the FEI in equestrian sport, and the FEI became earlier this year, based on this science, the first governing body to impose not only a linear but also rotational transmitted acceleration limit on the helmets it intends to approve. That was groundbreaking because that standard simply wasn't there until very, very recently. And it's not all about just developing things. We also need to be able to measure all of these things. One of the things that gets ignored in today's helmet testing is the effect of the neck. The neck is very important, particularly in women, because it turns out that it has a huge amplifying effect under certain angles, but the ratio of neck strength to head weight is one of the things that is fundamentally different between the two sexes and one that is getting ignored in design and in testing. And so we are also developing new methods at the Institute of testing helmets that account not only for the head, but also for the neck. And last but not least, the head is not on its own. It's actually a combined exoskeleton that is required to prevent injury. And we're now starting to work with governing bodies to look, the work of Raim and Hashem, on how we can think about injury with inflatables and deployables that protect the pose of the falling athlete in real time. So a very, very exciting start and a huge range of applications now coming our way. We are slowly expanding into understanding sleep, mental health, knee and ACL injuries, spinal cord injuries, having started with those key 3 pillars I've just shared with you. And I just wanted to share, under the Vice-Chancellor's program for sport in Oxford, I got to meet this young man who came to a lecture very much like this. And he stood up. I asked several of them why they were there. And he stood up and he said, I want to tell you why I'm here. It's very rare, very, very rare. And I said, why are you here? So he said, because I got concussed when I was playing football with some boys that were much older than me, because I'm quite a good footballer. I was put in the year above. And you know, one of those really big lads fell on me, and I don't remember much, but I know my mom and dad took me to hospital. And I said, well, that's great, isn't it? He said, yeah, they imaged my head, but then for the next few weeks and months, I kept having these conversations with doctors, and they didn't really seem to know what was wrong with me or how to manage me or whether I was ready to go back. And so then I went back, and I had headaches for a long time, so then they just took me off again. And at some point, arbitrarily, 7 weeks later, someone said I was ready to go back and play, and I should go back and play. He's the person we're doing this for. And we must never forget it. He and his parents, a lot of children like him, today this vacuum of information that exists on how to manage these injuries and how to take these things forward. In my first few years in Oxford, I got to meet this incredible man, Sir Roger Bannister. And one of the things he told me that I will never forget is, it's incredible how people will forever remember you for 4 minutes in your life and not the 35 years that followed. So unbeknown to most people, he was actually an extremely avid and enthusiastic neuroscientist. This was a subject very close to his heart. And one of the things we're very keen to emulate across engineering science and the Podium Institute is a fantastic model of the student athlete. So we have started the world's first doctoral training program. We have 21 full scholarship awardees today. Many of them are incredible individuals in their own right, from blues rowing athletes to our first MD PhD, a neuroscientist and neurosurgeon from Birmingham who just started his PhD, to a professional acrobat, actually doing an MPhil and a DPhil in cognitive neuroscience. We are set on developing the next generation of chief technology officers and chief medical officers, the next set of world leaders who will identify and solve those challenges of tomorrow. And so, in trying to build Oxford's future at the intersection between sport, science, and medicine, I hope to have convinced you today that there is a strong case for more sport, less injury through technology and evidence-based medicine. Thank you very much indeed.
So thank you very much, Constantin. It was a very enlightening talk, all the different bits coming together with common purpose. And I'm sure there were no hard, cold stares in this room for you. But, so we've got time for some questions. So the lady here, please. I think there's a microphone coming down to you.
Everybody here? Thank you so much. It was absolutely fascinating. My eldest brother is a doctor involved in rugby league. He should really be here and not me, but he's not. And his specialism, of interest is concussion. He's the chair of the rugby league concussion cognition panel. I think he said they use, and he's always talking to me about the new tech in what they use. And 15 years ago, they'd have someone taken off the field and assess them, and then they'd email the results to a lab in Australia who would look at them real time and then email back, and it's come a long way since then. I think they use Cognigram, he said, and he was telling me about the mouth guards and the acceleration and so on. One of the things which I think is improving, but I don't know if it's just rugby players, but they're desperate to get back on the pitch. They want you to pop their shoulder back in, they want you to stuff their nose with cotton wool and get them back on. And it's very difficult, and it was always his decision to say, actually, no, the results say, I'm sorry, you can't go back on. They'd be furious, and he'd get it in the neck. And now that's become a bit better because of World Rugby bringing in, certain thresholds for certain decisions. But I wondered what you thought about the with the advancement of this tech, how that will impact the actual regulations around. So it's not individuals making individual decisions for players, but saying, listen, I'm sorry, if your results have, say, the red light, you can't go back on, it's not my fault, and, you know, and that's that.
Well, you've just put your finger on the very heart of one of the challenges in doing this type of research. It's not just about having the science, it's also about being able to anticipate human behavior around it. And so you're right, the gold standard today for diagnosing a concussion is actually a doctor-administered cognitive test. What we've realized over the last few years is that athletes become very, very good at faking the polygraph because they know what tasks are coming, and they actually start overcompensating for those tasks, even though they're not necessarily okay. And there's, of course, all these untold pressures, particularly in the professional sport, of I want to go back on, my teammates need me, the club manager wants me to play because I'm one of their star players and we can't afford to lose this match. So this is where objective measurements are the only way to go. What you want is something with a red LED or a green LED, and if the red LED flashes, it's not up for discussion. And that's the thing that doesn't exist right now. I think bringing that objectivity will actually make the players safer, most importantly, but also the team doctors able to enjoy life a little bit more, because they won't be playing psychologist, they'll be playing doctor. And that's what we need.
It was a question. Let's go up to the top over there, please.
Neil, thank you for a fascinating talk. You talked about really the interaction of two different worlds, medicine and engineering. Sometimes you get medics who don't know what problems to articulate that need solving, or engineers that know what technology can do but don't know what problems are out there to be solved. How do you sort of foster communication between those two different worlds to generate real progress?
That's a really excellent question, and something we've been trying to do within the Institute of Biomedical Engineering here for the last 30 years. So it needs to happen at all levels. Specifically around the Podium Institute, we have a bi-weekly lecture and group meeting to which we invite not just engineering researchers, but actually every single doctor, biologist, chemist involved on every aspect of our research. And that means that every idea is illuminated from all of those angles in the internal discussions that take place. You heard me mention it very briefly at the end. To me, the most important and the most effective mechanism is we appoint, as doctoral students, medical doctors who have an interest in learning about technology and how to integrate them in their practice. So Sheikh is a very good example of a neurosurgeon. He's coming in to work on the biomarkers project. He understands the brain biology, but he'll be taking that upon graduation with him into his practice, into his consultant role in the NHS. And that's sort of the slower burn thing of training tomorrow's leaders and making sure they go out there with that multidisciplinary understanding in mind. And the third, of course, which is a very long-standing mechanism, are workshops and conferences. So next week's conference is a very good example. We have 140 attendees. It's about 45 sports governing body representatives, 50 engineers, 35 to 40 medical doctors, either team doctors or researchers from various hospitals around the UK and the world. These are the three primary mechanisms, and we hope to continue finding new ones because it's a continuous challenge.
Do we have one very quick question to finish with? The gentleman in the middle, I think, had his.
Hi, really interesting talk. I mean, just intuitively looking at some of that data, one sport you haven't mentioned is boxing. Now, that seems to me the perfect data supply, right? You've got 3,000 angles of data, video data. You've got multiple, concussion or blows. You can have data from the glove, from the head, from everything. So I'm interested you haven't mentioned boxing. Is that because you're not getting much engagement, or is there some other reason?
Boxing has actually been very good, and we have worked on boxing, and I'm sorry I couldn't mention everything today, but there's something very interesting about boxing, which is the concussion rate is much lower than you might expect it is, and that's something we can't fully explain to ourselves. And as I mentioned earlier, there is a significant role played by neck strength and the preparation for a potential impact. And I think boxing is a very interesting example of that, where not all the time, but the majority of boxers are actually pretty well trained and pretty well prepared to the punch coming in, and are therefore contracting their neck muscles. And that seems to be creating a different pattern of both mechanical force transmission and neurosignals when the neck is contracted, which is why one of the devices I showed on there, where you're doing on the various multimodal studies, measures and quantifies neck strength. And we're having a theory, and it's only a theory emerging at the moment, that there is actually a correlation between neck strength and neck training and the probability of concussion for an individual. One of the challenges with the hours and hours is, you're right, there's a lot of hours of data, but smart mouthguard data and actual volume of complete data set in boxing is remarkably scarce, because quite a lot of this happens in clubs that are very, very poorly resourced. So one of the reasons we started with rugby is because we have 13 super high resolution cameras pointing at them for broadcast quality matches.
Great. Well, thank you very much, Constantin. I'm sure Constantin will be happy to take your questions afterwards. I'm sure he'll hang around for a little bit, and Johannes as well. So thank you for giving today's Jenkin lecture. Very intriguing, exciting work, and we wish you and the Podium Institute the best of luck solving some of those challenges and problems. So thank you very much.
Thank you. Thank you all.